So I'm also sort of in the middle of a job transition at the moment. I recently joined Microsoft Research some months ago. So most of the stuff that I will be talking about today will be stuff that I did during my postdoc stay at ETH Zurich. So the title of my talk is Delta Quantum ML Potentials in Realistic Drug-like Space. And we've mostly been looking at delta learning approaches in what we consider a bit more close to reality drug-like space. Before I begin, I would like to provide some motivation of the things that I will present today, right? So I think that everyone that's present in this workshop today is interested in quantum mechanics, right? And that is because, I mean, quantum mechanics offers a fundamental description of both physical and chemical properties as well as phenomena, right? So the electronic structure per se is responsible as well for many drug-relevant properties, whether that be like transition probabilities and reaction energies, as well as other things as solubility. As we all know, like computation of good QM properties in cheminformatics using ab initio methods is pretty expensive, right? And I think DFT has been called many times the workhorse of computational chemistry. And many of the talks here and many of the people here have been trying to somehow make approximations to those approaches that are significantly cheaper than running these ab initio calculations, right? And as well, like many people here have been working on quantum machine learning for years, specifically like in the 90s and in the early 2000s, there was a lot of research concerning like hand-crafted descriptors in order to predict like quantum mechanical properties, whether that is like soft descriptors or FCHL. So hand-crafted descriptors in cheminformatics, and specifically in the context of DFT, have a super long history. And yeah, in the past couple of years, right, or 5 years or so, deep learning has taken the field by storm, right? Then we're starting to see all of these like neural networks with symmetries embedded into their design, with equivariances right at respect, rotations, translations, and as well as reflections naturally in their design. And these have taken the field by storm. And I mean, it's hard to go through Twitter nowadays and not see a new equivariant paper every once in a while that claims state of the art on QM9 or some other data set. I would like to provide like some sort of outline of the things that I would like to present today. The first one is I would like to present QMugs. QMugs is a data set that we've developed at ETH Zurich. It's sort of like a revamped QM9, if you will, because we were tired of seeing benchmarks on QM9. So QMugs is a database that we think addresses some of the previous like limitations of quantum mechanical databases, with observables computed at 2 different levels of theory, of which I will describe now. And then afterwards, I will describe this approach, which we name Delta, in which we try to do delta learning on both levels of theory that are computed on the QMugs dataset. So first let me present QMugs per se. So QMugs is a database that's completely open source, and it features QM properties computed for what we think is a biologically relevant subset of Campbell. We provide about 2 million conformers, corresponding to about 600,000 compounds. And we feature 2 different levels of theory in the database. We feature the semi-empirical level of theory GFN2XDB, which is from the green group, and a DFT level of theory with a hybrid functional as well as a single zeta Karlsruhe basis set. We feature about 32 QM properties, including weight functions, and compared to the state of the art or other databases that are out there, some of the advantages that this database QMugs possesses in comparison to those others is that mainly we feature bigger molecules. So we feature molecules up to 100 heavy atoms with a mean of 30.6 heavy atoms compared to the much smaller QM9 or anyone. We also provide multiple conformers per compound, which allows also learning of relative energies. We also believe that the fact that QMugs is extracted from a subset of Campbell enables research between electronic properties as well as biological activity. And here on the right, we're showing like some sort of Venn diagram that shows the overlap between QMugs and other popular datasets such as ANI1, QM9, and TopChemQC. And we see that the overlap is quite small. which is mostly related to the size of the compounds considered in this data set. I would like to maybe guide you a bit through the generation pipeline of the database. So we start with Campbell, and then we apply some activity filters. That gives us some raw miles. Then we do some cleaning of those miles. So we apply the RDKit standardization pipeline, and that provides. We also, have some heavy atom filters as well as some filter on the atom types, and that provides us with like some clean miles. Then we run some energy minimization using the Merck force field, and that provides us with like a low energy stat conformer, which we have for which you have one per compound. Then we use the GFM2 XTB software, specifically Crest, to run a metadynamic simulation for about 50 femtoseconds. For about 5 picoseconds, and we have structured it in between like 50 femtoseconds intervals. Then we do some k-means clustering on these coordinates, on these conformations, to have different clusterings of conformations. For each one of these clusters, we take the lowest energy structure from each one of these clusters, and then that provides us with like samples from different points in conformation space. Then we do some basic geometry validation checks, mostly regarding like bone lengths, checks on isomorphism, planarity of rings, things like that, to discuss some structures, and that gives us a maximum of 3 conformers per compound considered in the data set. And then we run some DFT as well as semi-empirical calculations using Psi4 and the XTB software. With the FNXDB specifically, we can compute biversional frequencies and as well as other thermodynamic data. With Psi4, we can compute wave functions in the form of density and orbital matrices. And with both of these softwares and levels of theory, we can compute atomic and molecular properties such as energies and other electronic properties. So one of the first things that we did was to compare the observables at both levels of theory, and in general, a correlation between XTB and the DFT functional that we chose is quite high. So for things like formation energy, dipole moments, rotational constants, and LUMO energy, correlations are over 0.9. But for others, such as HOMO energy and also for the HOMO-LUMO gap, we found the correlations to be still high, but not so as high as the others. And we'll see that this decrease in correlation will also have a performance impact when we'll try to do delta learning in the second part of this talk. Another thing that we wanted to do was to validate the geometry optimization pipeline that I previously described. And for that, we take 500 randomly chosen instructions from the QMugs data set. And what we did was essentially we compared how the geometries between the geometries pre-XTB and post-XTB optimization look like. And what we see is that the median is around like 1 angstrom, as well as run some full geometry optimization via DFT with the chosen functional to see whether the geometries that we get from XTB are somehow close to the DFT ones. And we see that most geometries fall below 0.5 angstroms in RMSD, which sort of confirms that this is a reasonable pipeline for geometry optimization. So in terms of the use cases that this database may have prospectively, the first one, and I guess more evident one, is that, you can use it for DFT observable prediction, right? The main advantage is that we do provide training data for what we believe is like previously unavailable chemical space. So we don't limit ourselves to 9 heavy atoms. This can be used also for benchmarking. It would be fantastic if we see people running their ML potentials on this database to see if they get like different results or different conclusions from what they get on QM9 or datasets. Then the second utility of the dataset is that since we provide wave functions, we can also think of one can also think of providing or developing like wave function learning pipelines, right? And for instance, one can think about directly learning orbital of density matrices in order to accelerate either DFT convergence or directly derive properties from the wave function. And the third one is that since we provide properties at 2 levels of theory, right, the natural approach is that we can do delta learning between the two levels of theory that we consider here, which is the semi-empirical approach XDB, as well as DFT. And this is what I'll be talking about for the rest of my talk. So at some point when we were developing QMugs, we thought that this was a good idea. So we named this approach Delta. So I've already some people have said to me that they don't understand the name Delta. We're not the greatest at naming things. So Delta is supposed to be like a mixture between Delta and DFT. So we do Delta learning on QMugs, and as you probably know, like in computational chemistry, right, you have this huge array of methods, right? You have things like force fields that scale linearly with a number of bases, to things like Apple cluster, which scale, I believe, with n⁷ the number of bases, right? So what we're trying to do is sort of like fill the gap between semi-empirical methods, the one that we're considering, XDB, and density functional theory, using the functional basis set that was chosen on QMugs. And for that, what we essentially do is that instead of trying to predict the DFT energy directly, what we try and consider is to learn the difference of energies or any other property in this database between DFT and the XDB baseline. To do that, we use an EN equivariant graph neural network architecture. It's from the lab of Maxwelling. So this is an architecture that is equivariant in the coordinates, but invariant in the node features. For the sake of this work, we only cared about the invariance in the node features because we're only predicting scalar values. And for the specific loss function for the energies, we do consider like a compound loss function, in which in the first term, we only consider like differences between absolute energies, and in the second term, we consider differences in relative energies for the same conformer. For different conformers of the same molecule. One of the things that we did, again, is to check whether this sort of pipeline worked, right? And so we checked this for many of the observables that we have for these two levels of theory, for formation energies, HOMO, LUMO, their gap, total molecular dipole, but we also focus on non-global molecular properties. So we also provide things like Mulliken partial charges, bond orders, and as I previously mentioned, we also measure relative energies. And we see that in most cases, like the approach seems to work significantly better than XDB, no surprise. I guess that the most interesting question to ask here is how delta learning performs against direct learning, right? For most of the subsets and the test sets that we're considering in this study, delta learning approaches in particular do tend to outperform their direct learning counterparts. The case is not so clear for instance, for like HOMO energy and Mulliken partial charges, where the difference is possibly not so clear. It's especially bad for HOMO energies, and this also relates to the fact of the correlation that we had seen before between XDB and DFT, where the correlation for at least HOMO energies was not as good as the rest ones. So of course, this wouldn't be like a QML talk if I didn't show some learning curves, right? So here we have like results at different training set sizes. So we go from just as little as 100 compounds to 1.6 million, and you see that, for instance, so the orange line there represents pipelines that were using the direct learning approach, and blue ones are the ones that are considering the delta learning approach. And one thing that can be appreciated here is that some of the endpoints, such as, for instance, LUMO energies as well as dipole moments, do tend to take more advantage from the delta learning paradigm than the rest of them. So, and this is what we're trying to summarize in these slides, right? So, a couple of slides ago I had shown correlations between observables between XDB and DFT. And in this plot, what I'm trying to show is whether there is a relation between that correlation and the amount of information that you can get from delta learning. And one of the things that we can see is that if we try and correlate these approaches, the observables where the correlation was the lowest are the ones that you can expect to gain the least from delta learning approaches. So for instance, in this case, right, for HOMO energies, direct learning was better, whereas for dipole moments, information energies, they do seem to take more advantage of it. This is more of a curiosity, if you will. So Also in this study, we also evaluated the performance of the direct learning pipeline of QMugs to generalize on bond orders for non-covalent interactions on larger systems. So we selected a bunch of larger systems. They contain some protein pockets as well as some systems like this beta turn of these hydrolases that we're showing up there, as well as a ubiquitin alpha helix. And we compute bond orders for, we run some DFT using the provided functional basis set, and then we compare the predictions from QMugs using direct learning. And in most cases, we do see that there is a correlation, but these are, let's say, more preliminary analysis. This is something that we're still actively looking into. One of the things that I guess we're the most proud of is that we put special focus on making these things available on an open source fashion, because I mean, if no data and no code is available, nobody will ever use this. So we created the Delta software, and everything is completely open sourced. All models are provided there. All data is also provided there. All of the data splits. It comes with a very permissive AGPL-v3 license. And one of the things that we also strive for is like ease of use. So we directly interface with OpenBubble readers. So if you're familiar with OpenBubble, then you can just plug in whatever molecule, whatever system you have in there, and get some predictions for the quantum observable that you that is of interest to you. Of course, PRs are welcome, and if you find any bugs, issues, etc., also more than welcome. So yeah, some takeaway points before I finish my talk. I would like to summarize and say that, in our view, QMugs represents a more exhaustive and, let's say, realistic database for the development and testing of, let's say, novel QML methods in drug-like molecular space. We provide both direct and delta learning, which enables both direct and delta learning approaches, as well as weight function learning. And in regards to the second part of the talk, we believe that the proposed delta QML approach obtains state-of-the-art performance with respect to DFT at a more manageable semi-empirical cost on QMugs. And in that regard, I believe that we are the first to test this paradigm on multiple QM observables plus atom bond level properties. And also, I would say that one of the main advantages of this project approach, in contrast to other people that are doing delta learning, is that we do open source everything, and I believe that is one of the main selling points. And with that, I would like to acknowledge some of my colleagues from ETH, mostly Clemens, which I don't know what he is over there, as well as Ken. So they were all the main driving forces behind this work. I'm just a figurehead. Marcus, who started the whole delta learning idea, as well as Gisbert Schneider for his support and funding. And I would also like to support to acknowledge the ETH cluster support, because they did provide like a lot of support, especially in the early days, and they were very kind, specifically when we told them that we wanted to take the university cluster hostage for 5-6 months to run these calculations. So special thanks to them. And with that, I would like to conclude, and if you have any questions, I'll be happy to take them now.
I have to say that's a great logo for Delta.
Hi, I really appreciated your talk. Thinking back to when you showed all the different XTB versus DFT features, I noticed that some of the blobs were kind of offset from the equal line, and I think those were the cases that you showed really strong performance, and some of them instead had the wrong slope. So in that latter case, did you ever try any methods where instead of predicting a delta, you predicted a scale factor?
A what factor again?
A scale factor, so something that you multiplied by to change that slope rather than a delta to just shift it.
No, we have not tried that, but that's something definitely interesting. Yeah.
Getting back to the old days of quantum chemistry levels of theory, where you just multiply by a magic number to get the right answer.
You might suspect what I'm going to ask you, but I'm not going to ask you that. I'm going to ask you something else.
Okay.
So what I'm going to ask you is, have you tried multi-fidelity models? We've seen that do great. So instead of delta,
okay,
because in delta, you end up having to pay the price for the original calculation all the time.
Yeah.
We found this to work, which is you train a first model to predict the chip output, and then do delta with that, meaning that you can sort of produce it from scratch.
Yeah.
And it has, I think, a flavor of sort of data augmentation, because you're not giving the model a lot more. But we found that to beat transfer learning, delta, so in general, sort of piping the two models, right? The first one gives you the XTB, and the second one goes from that to DFT. Have you sort of bumped into this?
No, we haven't. But I mean, I think this is also like in our minds. So if we get also like a proxy model for the semi-empirical approach, that's obviously like the first thing to try, right? And I think also one of the things that we would also potentially be interested in, no pun intended, is also to test like these delta n approaches in which you can start with like a very cheap method like a force field or something, and then go to semi-empirical, and from semi-empirical to DFT, and et cetera, right? So you can change these things in a very natural fashion, I would argue. I'm not entirely sure whether this field has been, or this specific thing has been explored yet. Yeah, Alexander?
One last question from Lois.
Why not just refit XTB?
Come again?
Why not just refit XTB to get you DFT accuracy? Just refit XTB model instead of correcting it for delta.
So what do you mean by refit specifically?
Learn new parameters that would give you DFT accuracy with the XTB Hamiltonian.
That would be another approach, yes.
All right, let's thank Jose again.
Yeah.